Okay, page 2 of vector applications. Write the gradient of the line in terms of components of the vector b. So when you have a two-dimensional line, remember that the slope is equal to change in y over the change in x. So when you have the vector b, if you have b1 and b2, remember that the change in y is at the bottom and change in x is at the top. So you would want to write b2 divided by b1 when you want to write the opposite change in y over the change in x. It would look like b2 divided by b1. Write the parametric equation of the line where t is a real number, where t is the real number is the parameter. So it would be x equals a, you would have the starting point a1, or the starting coordinate a1, and then you would have t times the b direction for the x component of the b direction, okay? And then y would be a2 plus t b2. And this is just following what we just did on the previous page, remember? So like the top equation is x equals a1 plus t times b1, and the bottom one is going to be y equals a2 plus t b2, and that's exactly what we wrote down here. Okay? We can convert the parametric equation to a line by equating the t values showed using the parametric equations from example 2. So we have these two parametric equations, and it doesn't look like what we're familiar with a line. Usually what we see with a line, we see like y equals 3x plus 2, or we see 3x plus 4y equals 12. These are equations of lines in Cartesian coordinates, and this one has a t in it. But so how do you get rid of the t? Well, we just solve for t and we equate them to each other. So for example, let's say we got x equals 1 plus 3t, and then we also have y equals 5 plus 2t. So first thing we're going to do is we're going to isolate the t. So x minus 1 equals 3t, and divide both sides by 3, and we'll get x minus 1 divided by 3, and that equals t. And then for this one we have y minus 5 equals 2t. And we divide both sides by 2, and now we'll have y minus 5 divided by 2 equals t. Okay, that is a mess. We'll rewrite the 2 there. Okay, so now we have two things that are both equal to t. We can set them equal to each other, right? Because t equals t. So we'll put x minus 1 divided by 3 is equal to y minus 5 divided by 2. And now we just need to put it in either this gradient intercept form or in standard form, and then that would be the equation of the line. So let's see, we could, for this equation here, we could multiply both sides by 6 to get rid of the 3 and the 2, and that would give us 2x minus 2 equals 3y minus 15. Okay, if we multiply both sides by 6, we're going to get that. Okay, and then we can put it in standard form by subtracting the 3y over to the left, and then we'll add 2 to both sides and get minus 13 on the right, and now we'll have standard form. So we could say 2x minus 3y equals negative 13. So we've now transformed the parametric equations form to standard Cartesian form for 2D. Okay, and that doesn't really make too much sense for other dimensions. It's convenient to use the parametric form for 3D, 4D, 5D, but for 2D sometimes we want to convert it to what we're used to. Vector equation of a line in 3 dimensions. This looks similar to this for 2D, right? Except for now we just have 3 dimensions. So now we'll put, instead of A1 and A2, we'll have A1, A2, and A3. We'll add t times, and then we'll have the direction vector, which is going to be in 3 dimensions also, B1, B2, and B3. Okay, so that's it. Parametric equations of a 3D line where, and I wrote where twice, sorry. t is a real number, then we're going to put x equals a1 plus t1b. Not t1, b1. Okay, and so the only thing different now, instead of a1, it's going to be a2, b2, and c3, I'm sorry, a3 and b3. a3 plus t b3. Okay. Number 1. Describe each of the following lines using a vector equation, parametric equations, and a Cartesian equation. So first, a line with direction 1, 4, which passes through 3, negative 4. Okay, so which one is A and which one is B? Well, it's the direction, it's B, and the point on it is A. So the vector equation, we've already gotten it, right? It's going to be 3, negative 4, and we could say like the vector r is equal to 3, negative 4, plus t times 1, 4. Okay, so that would be the vector equation. And then the parametric equation would just be like splitting this up into the top and the bottom. So we could write x equals 3 plus 3 plus t, because it's 1t. And y is equal to negative 4 plus 4t. Okay, so that is the parametric equations. Cartesian equations. Okay, now this is a little bit more tricky. We need to solve for t on both sides and equate them. Remember that? So, for example, the first one, y equals 3 plus t, that's not too bad. We can like easily change that into a equation where t is isolated. We just subtract 3 to the other side. And then this one here, let's see, we could subtract 4 to the other side. We get y plus 4 equals 4t. So t would just be equal to 1/4 y plus 1. And then we're going to equate the two. So we have x minus 3 equals 1/4 y plus 1. And then we can multiply everything by 4 just so that we don't have any fractions. And then we get 4x minus 12 equals y plus 4. And then we have 4x minus y equals 4 plus 12, which is 16. Okay, and so this would be our Cartesian equation. Okay, next example, or next problem. A line parallel to 3i plus 7j, which cuts the x-axis at negative 6. Okay, so if it cuts the x-axis at negative 6, that means one of the points on this line is negative 6, 0. Remember that if it cuts the x-axis, the y-coordinate is going to be 0, and the x-coordinate is going to be the x-intercept. Okay, so the vector equation is pretty easy. It's negative 6, 0 is the fixed point, and the direction vector is going to be 3 for the x and 7 for the y. So we're already done with the vector equation. And then, of course, the parametric equation is also easy. You just have x equals negative 6 plus 3t. And then you have y is equal to 0 plus 7t. Okay? And now the most challenging is to find the Cartesian equation. So we could do that by, we could try something different this time. Because remember, we know we can figure out the gradient by putting b2 divided by b1. So let's do that. We could like say b2 is 7 and b1 is 3, so we already have the gradient, right? And then we have the x-intercept, which is that. You guys remember point slope form, which looks kind of like this: y minus y1 equals m times x minus x1. Do you remember that? So we could put that. So we have y minus 0, because our point is negative 6, 0, and our m is 7/3, and here we have x minus a minus 6, which would be plus 6. Okay, so we're already in a Cartesian, this is already a Cartesian equation, but if we wanted to simplify it so that there were no fractions, we could multiply everything by 3. So we could have 3y equals 7x plus 42, something like that. And then we could move the x to the other side or the y to the other side and get something that looks more like standard form, like that. Okay? 3. Does 3 comma negative 2 lie on the line with vector equation r equals 2, 1 plus t times 1, negative 3? Okay. There's a couple ways we could do this. Let's do the most simple, which is we could substitute 3 comma negative 2 in the equation and see if there's any t which makes that true. Okay, so we'll put 3 negative 2 equals t 2, 1 plus t times 1 negative 3, right? And then we'll just check to see, is there any value of t which makes that true? So to solve this, let's see. What value of t would we put to make the top part true? If we had t equals 1, then the top part would be true, right? It would be 3 equals 2 plus 1. That would be perfect. Now, does t equal 1 work for the bottom too? 1 minus 3 is negative 2. It does. So t equals 1 is the solution. Yes, it works. So yes, 3 comma negative 2 does lie on the line when t equals 1. Okay. What about b? K4 lies on the line with parametric equations, blah, blah, blah. Find k. Okay. So we substitute k in for x and 4 in for y, and so we'll get k equals 1 minus 2t, and we'll have 4 equals 1 plus t. And then, so from this equation here, we already know that t equals 3, right? And so then we put this back in here, and then we say k equals 1 minus 2 times 3, which is equal to 1 minus 6, which is k equals negative 5. Okay, so k equals negative 5. 5. Describe each of the following lines using a vector equation and parametric equations. And let's see, A. A line parallel to 2, 1, 3, which passes through 1, 3, negative 7. So 1, 3, negative 7 is our A position vector, and parallel to blah, blah, blah means that that's the B. So we already know that our vector equation is R equals A, which is 1, 3, negative 7, plus T times 2, 1, 3. And the parametric equations would just be breaking it down into components. So it would be x equals 1 plus 2t, y equals 3 plus t, and z equals negative 7 plus 3t. Okay? All right. C. A line parallel to the x-axis which passes through negative 2, comma 2, comma 1. All right. So for this one, the A vector, position vector, is that, right? Parallel to the x-axis. So now we have to actually construct our B. Our B is going to be parallel to the x-axis. Parallel to the x-axis means that the x component is going to be a 1 and the rest of them are going to be 0, for example. Okay, so this actually wasn't too bad. It's the r vector is equal to negative 2, 2, and 1, and then we multiply b times t, which is 1, 0, 0. And if we want to make that into parametric equations, again, it's x equals negative 2 plus t, and then y equals 2 plus t times 0, which is just 0, and z equals 1. And that's it. Okay? Last one, number 7. Find the coordinates of the point where the line with parametric equations, blah, 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 meets the XOY plane, the YOZ plane, and the XOZ plane. What the heck does that mean, right? So basically, imagine that you have a 3D coordinate system where it's x, y, and z. When they say the XOY plane, they would mean the plane that contains the origin and the x-axis and the y-axis. So you can kind of see that they're talking about this plane right here, the flat one. All right, so if we want to figure out the coordinates when the line meets that plane, basically the definition of that plane is that z is equal to 0, right? So the question is, when does the z parametric equation equal to 0? So 0 equals 3 minus 2t. What is t equal to when z equals 0? Well, 2t is equal to 3. T is equal to 3 halves, okay? So t is equal to 3 halves, and so now it's easy to figure out what y and z are, because y is equal to 3 plus, and 3 halves is just 1.5, so we'll say 3 plus 1.5. So y is equal to 4.5. Z is equal to 3 minus 3 halves, which is just 3 minus 3, which is just 0, of course, because that's we defined it as 0, right? So y is equal to 4.5, z is equal to 0, and x is equal to 1 minus 1.5, which is equal to negative 0.5. Okay, so the coordinates of the point would be negative 0.5, comma, y was 4.5, comma, 0. Okay, what about the YOZ plane? The YOZ plane, it would be this one right here, this one that's kind of vertical that we're looking right at. Okay, so in that case, the x is 0, right? So when the x is 0, that means that the t value when x is 0 is going to be 1, right? And so when t equals 1, y equals 4. When t equals 1, z equals 3 minus 2, which is 1. So the coordinates for this one are going to be 0, 4, 1. Now you getting the idea? Okay, last one, the XOZ plane. So the XOZ plane is this plane here, which is kind of diagonal. Okay, so when in the XOZ plane, which coordinate is going to be 0? The y coordinate is going to be 0, right? So when the y coordinate is 0, we know that 3 plus t is equal to 0, which means that t is equal to negative 3. If t is negative 3, then that means x equals 1 minus a negative 3 is equal to 4, and z is equal to 3 minus 2 times negative 3, which is going to be 3 minus negative 6, which is 3 plus 6, which is 9. So now our answer is going to be 4, 0, 9. Right? And that's it.